Hello guys, today I'll be speaking on regular Falsi method or first position method under numerical analysis. Let's get into it. So we have this nice question here which says find the root of x e to the power x equal to 1 on the interval 0, 1 using the regular Falsi method. So we don't want to dive into it. How best can we be able to solve this question? So before we solve the question, we want to now look at a little background of fixed point regular Falsi method, how to derive this regular Falsi method, and then how does the algorithm of regular Falsi method of first position method actually works, and finding the approximated root. And then finally we'll get back to our question that we have seen. So this regular Falsi method is one of the bracketing iterative method in finding roots of nonlinear equations in numerical analysis. And then to get the approximated root, we fall on the principles of slopes or gradients. We continue to construct several slopes which will help us to obtain this approximated root, or will aid us in getting the approximated solution. And this method is noted to be based on Bolzano's theorem of continuous functions. And this theorem of Bolzano's theorem says if a function f of x is continuous on an interval a and b, and the functional value of a times the functional value of b is less than 0, then a value c belonging to the open interval a and b exists for which the functional value of c is equal to 0. Now we want to look at all that we are trying to say from the graph. So looking at the values, the interval that is given to us, a1 and p1, we first of all want to check another Bolzano's theorem to see if the theorem actually works. So we first of all check the functional value of a1 is going to give us something positive here. And check the functional value of b1 is going to give us negative. So this one from the graph even tells us that our root, which is the red spot here, actually exists. So if the root exists, then we go ahead to find our c value here. So first of all, we first construct our first gradient here using the coordinates a and the functional value of a, and a 0 because the y value at this very point is 0. C and then our c and 0, and then we look at b and then the functional value of b. So we now, after obtaining c, we check the functional value. If we check the functional value, it's going to definitely go to negative here, which is what we have as our b2 here, as our b2. And then we, based on the points that we have here, we construct another gradient here, which we happen to get another c value here. So we check the functional value here, it's going to be negative. So we continue to perform. So getting a negative value tells us that our root, because the functional value of a1 is positive. So since we happen to get a negative functional value here, tells us our root exists between a1 and then our b3 or c2. So we continue with this process until we happen to get an approximate solution. So from the graph that we have here, for us to construct a gradient, we can fall on either equation 1 or equation 2 or equation 3. Any of these three equations can still help us to be able to get what? Our c value. So using any of the three approaches, we can still get the formula for the regular Falsi method. So but we kind of fall on equation 1 to help us to get our regular Falsi method. So we rewrite the equation 1 as equation 4, and then our zero vanishes, which gives us equation 5. So getting equation 5, we cross multiply to get equation 6. So we then expand equation 6 to get equation 7. We then group like terms with a C, all the terms with the C on the left hand side, and then we factor out our C to get, after factoring out C, we will get our f of B minus f of A. We then divide through, which eventually we get our regular Falsi method as what, equation 9. So getting this regular Falsi method, now we can go ahead to perform our iteration. So first of all, like based on Bolzano's theorem for continuous functions, we do our checks, and then if we happen to get a negative value, tells us that way the functional value of A and the functional value of B, the product of it, if it's negative, it tells us our root exists. If there's none, then there's no need for us to worry ourselves. Or better still, there's a need for us to consider looking for a different interval. Okay. So if the root exists, then we can now go ahead and perform our iteration. And then we have seen, so to find our C, we fall on the first position, or the regular Falsi method. So after computing our C, we check the functional value. If this goes to 0, then that's bingo. The C is the root under consideration, the actual root under consideration. So, but if this condition fails, then we check the functional value of A times the functional value of C, the product of it. If it's less than 0, then tells us our roots exist between what, A and C. So then our old B is not needed again. So we'll reassign our C to B for computational purpose. If this condition fails, if the functional value of A times the functional value of B is positive, then tells us that the root exists between, if it's positive, then tells us our root exists between B and C. So there is a need for computational purpose as well. We have to reassign our C to A. So we continue this process until we happen to get a convergent value. We'll look at this iteration into details. So getting back to the question that we have seen there, we rewrite our f of x in terms of this. We know our a1 to be equal to 0 and our b1 to equal to what, 1. We then check the functional value of a, which is negative. Check the functional value of b, which is positive. Is the sign that we are interested in. It's not the actual value that we are interested in, but the sign. So this one is negative and this one is positive. So since it's positive, then we are convinced that our root C exists between this interval. So we can now go ahead to perform our iteration. We now call on the regular Falsi method to compute C. And then when we plug in our A and then B value into the method, it's going to give us our C1 here, which is 0.3679. We check the functional value here and it gives us negative. So it's giving us negative. We know that the functional value of A, which is what? The functional value of 0 gives us what? Negative. So it tells us that our root now exists between C1 and a B. So we now reassign our C1 as what? A2. And then we maintain our B1 as our B2 again. So which gives us a new interval. So now we now go ahead to perform our iteration again. And then we compute our C when we plug in our values into the regular Falsi method. After computing our C2 value is going to be 0.5033. We check the functional value of it. It gives us negative. So once it gives us negative, it tells us that okay, there is a need for us to reassign our root exists between our C2 and then B2. So we now have a new interval as what, A3 and B3, which is as this. We go ahead to continue to find our C3. We plug into the values into the whole of this, and it gives us what, 0.5474. We check the fractional value is still negative. So when it's still negative, then it tells us that okay, we need to forget of our A3 and then reassign our C3 as what, our A4, and we maintain our B3 as our B4. We continue this process until we get a convergent value. So this is the summary of this regular Falsi method. So when you are given the interval A and B, we check the fractional value and of A and B. Once the product of it is less than 0, then tells us our C root, the C which is the root exists. We find our C here. So in the first iteration, we find our C, which is this. We check the fractional value is negative. So once it's negative, tells us that okay, the fractional value of this one is negative as we have seen it. So we reassign it. We check find our C2, check the fractional value is negative. So we kind of forget of the old A and our B. Well, one thing that you have to notice is for the regular Falsi method, one point will remain constant while the other point will keep changing. So we know that the fractional value of B is constant. It's always positive. And then the fractional value of A keeps changing until we happen to obtain a convergent value, which is after a successive iteration, the fractional value under consideration is 0.5671. So this one has brought us to the end of regular Falsi method. It's pretty simple and it is easier to use than the bisection method, which both are bracketing methods, because this one point is remain constant. It's only one point that will keep changing. It's different from the bisection method, of which other points, either A or B, will change as you continue to perform the iterative process. So if you like this video, please don't forget to subscribe, like, or share. Thank you.